Hello? Hello? Okay, so can we start? Yes. Okay, so today is the third lecture of the mini-course Introduction to Ratner's Theory. And just a side remark of yesterday that I said something which is not true. Remember the definition of a lattice when I said that gamma is a lattice when the quotient has a measure which is invariant, which is G invariant, a probability measure which is G invariant. And I said that in the case that gamma mod, G mod gamma is compact, I called gamma to be a unimodular lattice. This term is not right. The term I wanted to say is uniform lattice. We call gamma a uniform lattice. Okay? So it's just an observation of the notation. Yesterday someone forgot this cell phone here. So does this belong to someone? No? Okay. So now, before proceeding, we are going to make a review of the things that we did in the last two talks. And so in the first talk, we saw that in hyperbolic dynamics, naturally there is the appearance of homogeneous spaces, which are the quotients of this special projective special linear group in two dimensions by a lattice, right? And when we looked for the algebraic description of geodesic and horocycle flows on this quotient, we got that the geodesic flow is a right multiplication by a hyperbolic matrix, and the horocycle flow is a right multiplication by a unipotent matrix, right? So the idea of yesterday was to try to abstract this situation to a general situation, which was to define flows on homogeneous spaces. So what are homogeneous spaces? They are quotients, G mod gamma, on which G is a Lie group and gamma is a lattice. Okay? In the situation, we can do ergodic theory because, as I said, the definition of a lattice tells you that you have an invariant probability measure, a G invariant probability measure. So you have invariant measures, so you have ergodic theory. Good. So in this case, we call this measure the Haar measure of the homogeneous space, and we are interested in analyzing the actions of subgroups of G generated by unipotent elements, just like the horocycle flow is generated by the unipotent matrix 1, 1, 0, 1. Okay? So we saw in the very end of the talk three definitions which were in the statements of Ratner's theorems. So the first definition was of a U homogeneous set. So what is a U homogeneous set? It is a homogeneous L space. So I call the U homogeneous set A. So it is a L space equals to XL. So by XL here, someone asked me what was that. So XL is nothing but the action of L on the element X when you run over all elements L of your subgroup. Okay? So it's a set. So we call it U homogeneous if it can be written like that, on which this subgroup L is a subgroup that contains U, it is closed, and X is some point of your space, right? So this is what we call homogeneous set. Good? So we had also the notion of U algebraic measure. And what is the notion of U algebraic measure? Well, it is a measure, and it is a measure which is the Haar measure of some U homogeneous set. So you get a measure, and you call it U algebraic if you can find a homogeneous space like that, a U homogeneous set, such that the measure is the Haar measure of the set. Okay? So the third definition was of U generic point. So what does it mean to be U generic? It is a point which is generic in the sense that you have equidistribution with respect to some measure. And the measure is some U algebraic measure. Okay? So we have these three definitions. They are very nice. They are very rigid. And Ratner's theorems, they say that orbits of actions of subgroups generated by unipotent elements are, if you close them, the closure of orbits are always U homogeneous. The other theorem says that measures which are invariant and ergodic under these actions, they are always U algebraic. And that says also that if you get the action of a one-parameter unipotent subgroup, because I remind you that in order to talk about equidistribution, you need to have the action of an amenable group. So let's consider, for example, a one-parameter unipotent subgroup of G. And the third theorem of Ratner says that every point is eugenetic. Okay? So you have these three rigidity results about U actions. Good? So what I want to do today is to, let me see what's this, okay. What I want to do today is to come back to the setup that we began with, to come back to hyperbolic surfaces. So in other words, we are considering a special kind of homogeneous spaces, which is this, SL2R mod gamma, where gamma is a lattice of SL2R. Okay? You remember that actually this is not the tangent space, the unit tangent bundle of a hyperbolic surface. I mean, if you want the unit tangent bundle of a hyperbolic surface, you should put the P over here. But I claim that there is no difference between putting the P or not. If you can get any sort of information about this kind of spaces, you can project it to the projective space and get the information about the projective version of this space, which is the unit tangent bundle. Okay? In the notes, there is a short section which actually explains this relation better. So from now on, I'm going to delete the P and to consider actually quotients of SL2R by gamma. Okay? Where gamma is a lattice. So when does the story begin? And it begins a long time ago. So I'm only going to talk about the horocycle flow. The geodesic flow began actually much before. The history of geodesic flows on hyperbolic surfaces begin with Hadamard, where he constructed some kinds of cutting sequences. He did symbolic dynamics for geodesic flows on hyperbolic surfaces. But for the purpose of this talk, we are going to discuss Headlands Theorem, which is the first main result with respect to horocycle flows. Okay? So Headlands Theorem says three things, and it says the following. First of all, it tells you how can the orbits of the horocycle flow be, and he proved that I'm going to call the orbit of the horocycle flow an H orbit. An H orbit is either periodic or dense. Okay? So just like saying again what I said many times in the last two lectures, this is in the other spectrum of the geodesic flow, because we know that in the geodesic flow you have horseshoes and so on. So here you have no intermediate situation between periodic and dense orbits. If some orbit is not dense, then automatically it has to be periodic. Okay? So he proved more. He proved also that the hard measure of the set is an ergodic measure. With respect to the horocycle flow. Okay? And he proved that in the specific case where X is compact, if X is compact, he proved that in the situation the horocycle flow has no periodic orbits. So if the horocycle flow has no periodic orbits, it means that every orbit of the horocycle flow is dense. So the conclusion is that actually H is minimal. Okay? So today we are going to see a proof of the second item here. And the proof is going to follow a more general setup of representation theory. We're going to see it in a while. Okay, so this was, I quite don't remember when this was. I think it was either on the 30s or in the 50s of the last century. But a long time passed, and after this long time, Furstenberg considered this special case on which X is compact. And he tried to go further, and instead of investigation the topological properties of the orbits, he tried to investigate the properties of invariant measures. And he showed that in the situation that X is compact, then the horocycle flow is uniquely ergodic. So the theorem of Furstenberg is that if X is compact, then H is uniquely ergodic. Okay? So, in principle, I had plans to prove this theorem today, but I was too naive to think that I could prove the theorem and the other things that I wanted to do today. So actually, we are not going to make a proof of this, at least not in the classical situation without the use of Ratner's theorems. Actually, we can prove this using Ratner's theorems and Headlands Theorem. So here is a proof of Furstenberg's theorem using this big black box, which is Ratner's theorems. So how do you prove that such thing is uniquely ergodic? Well, first of all, you get an ergodic invariant measure. So let mu be an ergodic H invariant probability measure. So if you have this, and you know that the horocycle flow is a one-parameter closed subgroup generated by unipotent elements, you could apply Ratner's measure classification theorem to conclude that this measure mu is actually U algebraic, right? So if it is U algebraic, what does this mean? This means that the measure is a Haar measure. It's a Haar measure on some orbit. But if you use Headland, you know that the orbits, the homogeneous sets here, are either closed orbits or they are dense. But you know more. You know that if the guy is compact, then this orbit has to be dense. So by Ratner, mu is equal to mu of XL, mu A, for some U homogeneous set A. But you know that by Headland, the orbit of the guy has to be dense. So by Headland, the only homogeneous, U homogeneous set that you have is X itself. So by Headland, you get that A is equal to the whole set X, and then this means that the measure mu that you begin with has to be the Haar measure of the big set. So you get unique ergodicity. Okay? So this is a proof using to show the strength of Ratner's theorems. And okay, so we are in good shape. We know the situation, the measure classification when the quotient is compact. But no. Good? Okay. So, okay. So now that we know the situation on which you are compact, let's ask now about the situation on which you are not compact. Right? So Headland actually checked that in the situation that you are not compact, you always have periodic orbits. For example, going again to our nice guy that we have here. So this is the representation of a periodic orbit of the horocycle flow on the modular surface. So we know that guy, that description of that region is a fundamental domain of the action of SL2Z on the hyperbolic space. And if you consider the unit tangent bundle of this fundamental domain, then this gives you a fundamental domain of SL2Z inside SL2R. It's basically that. I mean, it's actually of PSL2Z inside PSL2R, but if you lift, then you get of SL2Z in SL2R. So what happens if you begin with a vector which is vertical pointing upwards, and you begin to apply the horocycle flow on this hyperbolic surface? So what you can conclude is that it actually goes parallel. The action of the horocycle flow goes parallel because you know who are the horocycles here. And because of the identification that you have of the left vertical line with the right vertical line, this means that you have a closed orbit. Okay? So in other words, you could see the representation of this something like this. Your space, something like this. And if you begin with a point here, you get a closed orbit. So you get many closed orbits. Actually, for any sufficiently vertical, for any horizontal segment sufficiently up, you can observe that this gives you a closed orbit of the horocycle flow. So, for example, you have no such situation, because if you have closed orbits, then you have measures supported on these closed orbits. So for sure, you don't have unique ergodicity. So what did Dunny and Smiley prove? They proved that this situation of orbits, of measures supported on periodic orbits, is the only obstruction for unique ergodicity. In other words, they proved that if mu is H invariant and ergodic, then either mu is the Haar measure of X, or mu is supported in a periodic orbit. Okay? So you have this dichotomy, which didn't occur when you had a compact space. So again, we can get a proof of this theorem using Ratner's theorems and Headland's result. So let me sketch the proof, and it follows the same lines, because if you get an ergodic measure, ergodic H invariant measure, you know that it should be the Haar measure of some U homogeneous set. But you know that U homogeneous set has to be either periodic or dense. So it means that the measure has to be supported on a periodic orbit, or has to be the Haar measure. So I'm going to actually leave the proof as an exercise, which is just to fill up the words that I just said. Okay, so the story about hyperbolic surfaces more or less ends here. These are the three theorems that I would like to tell. And they were all proved, of course, before Ratner's theorems. I think that Dunny and Smile was proved in 78, if I'm not mistaken. Actually, I can check here. No, it was in 84, and Furstenberg's was proved in 73, and Headland was proved in 36. So it was quite a big gap between this and this. And also between this and this. And Ratner's theorems were proved in 91. Okay, so what do I want to do today? What I want to do today is to prove actually that the geodesic flow and the horocycle flows are ergodic with respect to Haar measures. And actually we are going to prove more. We are going to prove that they are mixing with respect to the Haar measure. And why am I proving, why instead of proving Furstenberg's theorem, I decided to prove this? Because on these proofs, there are involved many concepts which are important for all the situations. And the concepts are, the first one is Mautner's phenomenon. We are going to discuss Mautner's phenomenon for the group SL2R. And the second one is a nice theorem which makes you go from ergodicity to mixing automatically, which is Hauer-Moore's theorem. So we are going to discuss these two theorems in the situation of SL2R. But in order to discuss this, we have to know more information about SL2R. So this is what I'm going to do in the next minutes, is to discuss more about the group SL2R. So part 2. Okay. So what did we see so far about SL2R? Do you remember something about SL2R? At least the definition of SL2R? Huh? Yes. Yes, they give rise to Möbius transformation. But on the algebraic perspective, what do we know? We saw a few subgroups of this group, right? We saw, for example, the rotation subgroup. It is a compact subgroup, right? It is isomorphic to the unit circle. We saw also A, the diagonal subgroup, which is isomorphic to R if you send lambda to log lambda. We saw also two unipotent subgroups. The first one was U plus, which is actually the subgroup that generates the stable horocycle flow. And we saw the one that generates the unstable horocycle flow, and I denoted it by U minus. So it's the set of matrices 1, 0, S1. Okay. So this is compact rotation subgroup. This is isomorphic to R. It's the diagonal subgroup. This is isomorphic to R and also U minus. And both of them are also isomorphic to R. Okay? They are the unipotent subgroups, U plus and U minus. So I want to tell you two properties about these subgroups and the relation of them with SL2R. And for that, I have to introduce a new subgroup. I don't know if I introduced that before. But A plus is a subgroup of A, which is given by the... It's not a subgroup, I'm sorry. It's a subset. It is given by the diagonal matrices on which lambda is actually bigger than 1. Okay? Bigger than or equal to 1. Okay? Okay, so the first thing that I would like to show you is what is called the Kaftan Decomposition. And the Kaftan decomposition tells you that you can write, so this is a lemma, that each element of SL2R can be uniquely written by the product of an element of K times an element of A plus times an element of K again. Okay? So, how do we prove such thing? Huh? How do we prove, for example, the existence, the equality? How do we prove the equality? I'm not worried right now about the uniqueness of this representation. Just the equality of sets. Any guess? Mario? So, we could, SL2R, we know, for example, what someone said there, that they generate Möbius transformations, right? And we know that Möbius transformations are isometries of the hyperbolic plane. So let's consider the action of SL2R on the hyperbolic plane and try to do the following. We know that SL2R, you can have an element of SL2R. Let me try to explain this better. Okay, so if you start with a reference vector, which is the vector, which we always fix this vector here, you can get any other vector of the unit tangent bundle of the hyperbolic space by applying the derivative action of SL2R on this vector, right? So the way that we are going to get that equality is doing the opposite. We are going to start with any vector in the unit tangent bundle of the hyperbolic space, and by applying an element of K, then an element of A plus, then an element of K, to bring it back to here. Okay? This is gonna tell us that this equality holds. So by looking at the hyperbolic action of SL2R on the hyperbolic space, we are going to be able to check that equality. So now the goal is to learn to manage how to get any vector in the unit tangent bundle and send it by successive iterations of an element of K, one of A plus and one of K. So how do we do that? So if you remember, I said something very special about K in the first lecture, that K is the stabilizer of the identity. And because it is an isometry, it preserves the circles around the identity, right? You fix the identity, then you should preserve the circle around the identity. So get any vertex in the unit tangent bundle here, let's say with basis on a point Z, and draw the circle which has center in I, and this I'm going to call, which has center in I and passes through Z. So this is a circle like this. Something like that. Let me draw this again. So we draw the circle, something like that. Okay? So the circle intersects the y-axis in 2 points. Consider this one to be the point we are looking for. So Z, V, I, and let this point to be W. Okay? So first of all, you could, because K fixes I and it preserves the circle, you can get a K that sends the base point Z to the base point W. So by the application of the derivative of k to this point, to this vector, what you get is a vector whose base point is w. So you get a vector here. Okay? So now you have to apply an element of A plus. But an element of A plus is a dilation. And is a dilation by, because you are like this, you are a dilation by something which is bigger than 1, right? So instead of considering this point, we are going to consider the point below. So let's change this point to this point. Because now, if you consider the point below, when you apply the element of the rotation group to this guy, so that z goes to w, you get a vector here. And then you can apply an element of A plus to send this base point w to the base point I. Because you know that as a dilation, it is a positive dilation, dilation with ratio bigger than 1. So because this guy is below here, you can make this. So you get a vector which is with base point in I, pointing somewhere. Again, because k fixes I, it acts by rotation on the tangent space of I. So there is a new element of k that makes this rotation and sends this vector to this vector. Okay, so if you begin with v equals to v1, you apply an element of k, you get some v2. You apply an element of A plus, you get something like v3. You apply an element of k again, you get I. So this picture shows that this decomposition is true. Any question? Okay, so everybody's convinced. The other property about SL2R that we are going to use today is that actually SL2R itself is a subgroup generated by unipotent elements. So the other lemma is that SL2R is generated by U plus and U minus. So the lemma is that SL2R is generated by U plus and U minus, okay? And I'm only going to tell you how to prove this. Well, for that situation, we use the hyperbolic action on the hyperbolic space. Here, you could use actually the linear action of SL2R in the plane, in the Euclidean plane, and to try to do the following, to try to get, so the linear transformation is associated to a basis. Let's say the basis that the E1 and E2 are sent to. So you could associate any element of SL2R with a basis on the plane which has determinant equal to 1, which has the area of the parallelogram is equal to 1. So the idea is to apply elements of U plus and U minus to send any of such bases to the canonical basis. Okay? And once you know the properties of U plus and U minus, for example, that U plus acts by translation on horizontal lines, but the only one that it does not act by translation is the x-axis. And reciprocally, that U minus acts by translation on vertical lines, you will be able to show that you can send any such basis like this, on which the parallelogram has area 1, to the canonical basis. And once you get this, you are done. Okay? So these are the two properties about SL2R that we are going to use today. And now we are going to talk about mountainous phenomenon. So mountainous phenomenon, it is an analytical tool that is used to provide extra invariance. And you are going to understand why in a few minutes. But in order to state this guy properly, I should first tell you what is a representation. So let's discuss a few things about representations. And to discuss about that, I will have to consider, first of all, a group, G. I will have to consider a Hilbert space. And just to simplify the notation, let us consider all linear transformations on this Hilbert space by GL of H. So GL of H are the linear maps. Let's call it endomorphisms of H. Okay? So these guys here, not the endomorphisms, even better, the automorphisms. Okay? So, we have a group G, and we have a Hilbert space. Once we have a Hilbert space, we have the set of automorphisms of H. This guy is also a group, right? By composition. So we have two groups. And the representation is nothing but a homomorphism from G, from that group G, to this guy here. So, a representation well, it's a representation of G on the Hilbert space R, is a homomorphism pi going from G to GL of H. So, in other words, you have for each element of the group, we associate an automorphism of H, which I'm going to denote by P of G. So this is a linear invertible transformation of my Hilbert space H. Okay? And the notation that I'm going to use, I forgot to say no, I didn't forget to say anything. So we associate this. The notation is that this is the evaluation of this linear transformation at some vector of H. Okay? So we said that it is an homomorphism. So what does it mean to be a homomorphism? It means that if you get this linear transformation associated to a point, to an element G, and you compose it with the linear transformation associated to the element H, another element of H, this is equal to the linear transformation associated to the element GH. Okay? So this is the homomorphism property, the group structure property. Okay, so can someone give me an example of a representation of any group? No? So we already saw one yesterday, but it's more complicated. So for example, what happens if you have a measure-preserving transformation here? Has someone heard about the Koopman-von Neumann operator? So what is the Koopman-von Neumann operator? It's something that I'm going to define by UT, and it is a map from square integral functions to itself that gets a function, and it composes it with the map T, right? So this guy here is a Hilbert space. And this guy here induces, so it induces a representation of Z on this Hilbert space. Okay? How? Well, pi n of a function f is f composed to t to the n. Okay? So we have seen before representations. So you could actually generalize this to any group action. So indeed, if G acts on a measure space X mu by measure preserving transformations, we can define the Koopman-von Neumann representation. And who is this? It's a representation pi that goes from G to GL of L2 X mu and it is defined by how is the action of what is the automorphism that I'm defining by the point G. So I should consider it applied to a function, and it is a new function such that when applied to a point X, it gives me the value of X G minus 1. Okay? So I'm considering a right action on the space, and because of that I'm putting the G minus 1 so that this property here of the group structure is preserved. So we have this. But note that we didn't even use the property that these guys are measure-preserving transformations, that the action of the group is measure-preserving. So actually what happens with this representation, in the case that you are acting by measure-preserving transformations, is that the representation has an extra property. And this extra property is that it is a unitary representation. So the definition is that pi, so pi is called a unitary representation if each linear transformation is a unitary transformation on your Hilbert space. Okay? This means that if you want to consider the inner product of the image of two vectors, you can just calculate the inner product of the vectors that you begin with. You're going to get the same result. Okay? So in the case that you are acting by measure-preserving transformations, the Koopman-von Neumann representation is going to satisfy this property, and this is just a change of variables. Right? So this is what we call unitary representation. And I want to talk about another property of representations, which is the following. assume that actually G acts here by continuous transformations. So if it actions by continuous and, of course, measure-preserving transformations, first of all, because it's measure-preserving transformation, you're going to have a unitary representation. Because you are acting also by continuous maps, then this Koopman von Neumann representation is going to have an extra property, which is to be strongly continuous. So pi is called strongly continuous if for every sequence that you are converging to some element of G in G, it holds that if you look at the image of a vector V under this sequence, this is a vector of your Hilbert space, and it is going to converge to the image of V under the limit. Okay? So basically, it's just like limit. It's just like that the limit can go inside the argument of pi. Limit of this, you put the limit inside, but the limit of Gn is G, so you have this property. This is what you call strongly continuous. And as an exercise, I'm going to leave to prove that if G acts on X mu by continuous measure-preserving transformations, then the Koopman von Neumann representation is unitary and strongly continuous. Okay? So these are the two properties of these representations. Okay. So the good thing about the Koopman von Neumann operator, in the situation that you have one measure-preserving transformation acting, is that you can translate many properties of the action itself in terms of the Koopman von Neumann operator, right? For example, to say that T is ergodic is the same as saying that any invariant vector under this transformation here has to be constant, right? So even better, if we consider from now on the Koopman von Neumann operator defined on the functions which are square integrable and have zero average. So from now on, put n 0 on these guys. Okay, so to say that T is ergodic is the same as saying that the only invariant function or invariant vector of this automorphism is 0, right? Has to be constant, it has to be zero average, has to be 0. And the same, you have the definition of actions in general. What is for an action to be ergodic? So the G action is ergodic if and only if the only invariant, G invariant function square integrable function are constants. Well, if you restrict yourself to functions of zero average, this means that if and only if the only fixed vector of the Koopman von Neumann representation is 0. Okay? So this is the definition of ergodicity. And we could abstract this to general representations. You could say that the representation is ergodic if and only if the only fixed vector of it is the 0 vector. Okay? So a representation pi that goes from G to, in general, to GL of H is ergodic if, when you consider a vector V that satisfies this equality for every G in D, this directly implies to you that V has to be 0. Okay? Okay, so we can abstract the notion of ergodicity to representations. So what about now mixing? What does mixing tells us? So in the terms of the Koopman von Neumann operator, in the situation of one transformation, we know exactly what mixing means. So for example, if you restrict yourself to L2 here, so let's delete here. So for mixing, we must have that this inner product of F with UTN of G goes to 0 for every F and G in L2 0 x mu. Right? This is a translation that mu of A intersection T minus N of B converges to mu of A times mu of B. In the case that you restrict yourself to functions of 0 average, this inner product has to converge to 0. So we could abstract this notion to representations and say what is for a representation to be mixing. And for that I have to introduce what are matrix coefficients of the representation. So given two vectors V and W of H, the matrix coefficient of pi with respect to V and W is the function f VW, subindex VW, that's defined from G and takes values on R. And this is defined by the inner product of pi of G, V, W. Okay? So for example, if you have only one transformation, then this is the matrix coefficient of the Koopman von Neumann representation associated to F and G. So we can translate the notion of mixing to say that an action, a measure preserving action, is mixing if and only if the Koopman von Neumann representation is mixing. So you have these associate definitions of mixing. Okay, so now I'm going to state what is Maltner's phenomenon and Haber-Moore's theorem, now that we have all the background necessary. So what does Maltner's phenomenon says? And I'm going to state it for SL2R. And it says the following. It says that if you consider pi, yes. So if pi is a representation of SL2R, is a unitary. Every linear transformation is unitary. And so let pi be this. Be a unitary and strongly continuous action. Not action, representation, sorry. Okay? So we are in this situation. You have a unitary and strongly continuous representation of SL2R. So the assumption is that if you get some element of A or some element of U plus that fixes any vector, then actually this vector is fixed by every element of the group SL2R. Then pi of h of V is equal to V for every V in SL2R. Remember that I said that Maltner phenomenon is something that gives you extra invariance. So the extra invariance is exactly this. So you are assuming that you have a vector, which is in H here, which is fixed by the linear transformation associated to an element G, and the assumption is that G is either diagonal or is unipotent, is in the unipotent subgroup. And the conclusion is that this vector V should be fixed not only by G, but by every element of SL2R. Okay? Questions? Okay. So, how do we prove this? We have two cases. So we have to divide in two cases, right? So let's divide in the cases where G belongs to A and G belongs to U plus. I'm going to postpone the statement about... No, I'm not. I'm going to tell about the statement of Hauer-Moore right now, because otherwise you are going to forget what is a matrix coefficient. So let's call this theorem. And let's call also Hauer-Moore theorem. Hauer-Moore is something that I said that allows you to go from ergodicity to mixing, right? So the assumption that you have is that, again, you have some unitary strongly continuous representation, B, unitary, continuous, and is strongly continuous. Representation. I said that it's something that makes you go from ergodicity to mixing. So let's also assume that it is ergodic. Okay? So I forgot to say something about matrix coefficients that I'm going to say right after I state the theorem. So the conclusion here is that pi is actually mixing. And what do I mean by mixing? I mean that for every V and W in H, the limit of the matrix coefficient associated to VW at G is 0, but the limit taken on elements of the group that go to infinity. Okay? So I just have to define what is for an element of the group to go to infinity, and we say that a sequence goes to infinity in G if for every compact subset of G there exists some n0 for which such that Gn does not belong to K for every n larger than n0. Okay? So you escape from compact subsets. So if you have a sequence that escapes from compact subsets, you say that the sequence is going to infinity in the group. And to say that a representation is mixing is to say that if you fix two vectors of your Hilbert space, then the matrix coefficient associated to these two vectors as the element of the group goes to infinity, this has to go to 0. Okay? For example, the natural notion, the classical notion of mixing of one transformation, to go to infinity in the group Z is the same as taking n to go to infinity, the powers that you are taking. So it's exactly to say that f, the inner product of f with ut to the n of g goes to 0 for every f and g square integrable and of 0 mean. Okay? So these are the two theorems that I hope to prove in the next half an hour. And now it's time to ask about the notions involved in the proof, in the statements of the theorems. No? Okay, so let's go to the proof. So, proof of Ratner phenomenon. So the idea of proof of Ratner phenomenon is actually, again, to use the fact that the geodesic flow renormalizes the horocycle flow. And the fact that we use is a lemma that I'm going to state in a second. So first let's write here that we are considering the first case on which G belongs to A. Okay? So G belongs to A. Okay. So what does it mean for, so G is in the diagonal subgroup. So it's just like, how do you say? I'm sorry, I had to assume actually also that G is not the identity, because if it's the identity, this happens trivially, right? So if G belongs to A or U plus and G is different from the identity, satisfies this, then that happens. So what does it mean for the geodesic flow to renormalize the horocycle flow? It means the following, that if you consider this element of A, and you are assuming that it's different from the identity, so it should be something which is like lambda 0, 0, lambda minus 1, where lambda is different from 1, right? So let's assume that lambda is actually bigger than 1. So assume that G belongs to A plus, that subgroup that we defined in the beginning. So the translation in mathematical terms of the fact that G renormalizes the horocycle flow is the following, is that G to the n, H, G to the minus n converges to the identity in SL2R. So why is that so? So this is a claim, and it is simple to check, because if G is equal to lambda 0, 0, lambda minus 1, where lambda is bigger than 1, and I'm sorry, this happens for every element of U plus. The geodesic flow renormalizes the horocycle flow. So the proof is that if you get G to be equal to this and H to be equal to 1 as 0, 1, then g to the n, h, g to the minus n. Actually, I have to change these guys here. So g to the minus n, g to the n is equal to, after you do the calculations, 1 s lambda to the minus 2 to the minus, not minus 2, but minus 2n, 0, 1. Okay? So if n goes to infinity, this goes to 0. Lambda is bigger than 1. So this goes to the identity as n goes to infinity. Okay? So this is the translation of the fact that the geodesic flow renormalizes the horocycle flow. And how do we use this? Whenever you are in this situation and G is fixing a vector V, I claim that this vector is also fixed by H. So the fact that I'm going to use, and sometimes it's called Ratner lemma, but we are going to have a few of them today, so I'm going to call Ratner lemma 1, is that assuming that also pi is unitary and strongly continuous, if Gn h Gn to the minus 1 converges to E, and pi of Gn, G sub n, of a vector V is equal to V, then pi of H at V is equal to V. So if we prove this fact, we can conclude, we are assuming that V is fixed by G. So because G renormalizes an element H of the unipotent subgroup, we are going to conclude that H is also fixed by, H also fixes V. So every element of U plus is going to fix V. And the proof of this fact, how would we prove something like that? We have to use the conditions of the representation. We have to use that the representation is unitary and strongly continuous. To use that it is strongly continuous is actually here, right? I mean, the definition of strongly continuous means that if you have a subsequence converging to another element of the group, then you could pass the limit from outside to inside. So in other words, the strong continuity tells us that if you consider the limit of this guy, it is going to be equal to V, right? So it tells us that the limit of this guy is 0. This is what strong continuity means. But before using that, let's just rewrite this in a better situation. Let's try to clean the GNs from one side and from the other side. Well, to clean the GN from here is very easy. Why? Because if pi of Gn, if Gn fixes V, Gn minus 1 also fixes V, because you have a group action. So this is equal to pi of Gn, H of pi of Gn minus 1, V. Right? Right? We know that this is V, so change it to V. So this is equal to this. But we know also, we use it here strong continuity. We have to use also that the representation is unitary. So representation is unitary, actually we could apply pi of Gn minus 1 here. And because pi of Gn minus 1 is unitary, it preserves the norm of vectors. So if you apply pi of Gn minus 1 on this expression, what you get is that on the left side you get pi h of V, and on the right hand side you get again pi of Gn minus 1 of V. But again, Gn is fixed by V. Gn fixes V. So this guy is also equal to V. So what I just showed is that this is 0. right? Passing through limits. The limit of this, which we know that is 0, so the proof begins here. 0 equal to the limit of this, equal to the limit of this, equal to this. So this tells us pi h of v equals to v. Okay? So by this fact, and because G renormalizes H of this expression, if you call the G sub n on the fact by G to the minus n here, and we apply that fact, we conclude, because we are assuming that pi of G fixes V, we conclude that pi of H also fixes V. So, by the fact, pi of H of V is equal to V for every H in U plus. Okay? So we begin with a vector which is fixed by only one element. The property is that this element is a diagonal element. This very property guarantees to you that V is fixed by many elements, by any element of this U plus. But U plus is no different from U minus. So we can conclude analogously, and the analogously is just changing G to the minus n to G to the n there. We exchange the order of the G's there. Analogously, we show that pi of H of at V is equal to V for every H in U minus. So if you have a vector which is fixed by every element of U plus and every element of U minus, are we done or not? Why are we done? We are done because I showed to you on the properties of SL2R that U plus and U minus generate SL2R. So to show that a vector is fixed by an element, by all elements of SL2R, you just need to show that they are fixed by some generators of this group. And we just did. We get that? Pi of H at V is equal to V for every H in SL2R. Okay? Nice. So we started with only one guy that fixes the vector, and we conclude that all of them preserve. So this concludes the case 1. And now the case 2. The case 2 is that G belongs to U plus, and G is not the identity again. Okay? Well, if the vector V was going to be fixed by all of U plus, then we would be in a better shape. But it's fixed by only one element of U plus. So what do? We have to get extra invariance. Elements of U plus, they do not renormalize. Sérgio? In the case that lambda is not bigger to 1, I change the signs here. Yeah, because instead of being lambda to the minus 2n, I would get lambda to the 2n. And now lambda is smaller than 1. Then I make n go to infinity. This also goes to 0. Okay? Okay, so the idea of case 2 is to try to, from this assumption, to try to get an element that actually belongs to A plus or to A that fixes also the vector V. So the idea is to reduce the case 2 to case 1. Once we can get one element that fixes V and this element belongs to the diagonal group, then we can apply case 1 and conclude the proof. So the proof is gonna use another kind of Mautner lemma again. but I'm just going to write here what I want to prove. So assume that your G, well, it is in U plus, so it can be written as 1S01. And because G is not the identity, S is different from 0. Okay? Yeah. So note that G to the minus 2n times this matrix 1, 0 minus 1 over 2ns 1 times the matrix G to the n is just a calculation of matrices. This gives you 2, 0 minus 1 over 2Sn 1/2. Everything here is well defined because S is not 0. And if you calculate using that G is equal to that, you get that this product here is equal to this. Okay? So we are more or less similar, in a similar situation than this. The difference is that the conjugation is not a conjugation. On the left side you have G to the minus 2n, on the right side you have G to the n. In the middle, you have something which is actually converging to the identity. But the good thing is that on the right-hand side, you have something which is converging to an element of A. It's converging to the diagonal matrix 2, 0, 0, 1/2. So, if we succeed to prove some fact which is similar to Mautner lemma 1, which I'm going to call Mautner lemma 2, which is the following. So if you have Gn, you have Hn, you have Ln, and this is converging to an element K, and you assume that, so if many properties hold, first this one, second, that the guy in the middle is converging to the identity, third, that pi of Gn at V is equal to pi of Ln at V is equal to V. Okay? Then pi of K at V is equal to V. So I can get extra invariance also on this way. And why, once we prove this fact, we are done? Well, because V is fixed by this guy here. V is fixed by this guy here. This guy is converging to the identity. And this guy is converging to a diagonal element. So the conclusion of the fact is that V is also going to be fixed by this diagonal element. And then we reduce to the case 1, right? So the proof of this fact I'm going to leave as an exercise. But it is exactly what I did here. Just with changes. Instead of Gn to the minus 1, I put Ln, and I send to the, and I use the invariance, and then I use that it is unitary, and I use that it's strongly continuous, and I get the result. So we are reduced to the first case. Okay? This is what is called Mautner phenomenon for SL2R. Any question? So it gives extra invariance because we began, so the assumption of Mautner phenomenon is that pi G of V is equal to V, for some G, there is only one G, if either G belongs to A or to U plus, then the conclusion is that V is fixed by all elements of the group. So it gives you extra invariance. The invariance of this vector by the action of the elements of the group. Did I answer? Okay. Same thing. Same thing. So here is a dynamical consequence of Maltner phenomenon, which is included in Headlands Theorem. So I'm going to also to state it as a theorem, is that if G, so if X is a hyperbolic, is the unitangent bundle is a hyperbolic surface, actually, and G belongs either to A or it belongs to U plus, then the Z action induced by G on X is ergodic. What is the Z action? It's just the iterations of powers of this element G. And so we have a right multiplication on this guy here, right? And why is this theorem consequence of Maltner phenomenon? Because you could just look at the Koopman-von Neumann representation. And you know that because SL2R acts transitively here, the Koopman-von Neumann representation has no invariant vectors other than 0 itself. So if you consider a vector which is a function, which in other words a vector, which is invariant by G, and G belongs to A or to U plus, then you know by Maltner phenomenon that this function is invariant by every element of the group. But because the group acts transitively on this quotient, this means that the function has to be constant. The function being constant and having 0 average, the function has to be 0. Okay? So this is the proof of the theorem. It should be called a corollary. And in particular, we conclude that the geodesic and horocycle flows on X are ergodic. Okay? So this is the first thing I told you I should prove today. I guess I cannot prove the second thing, which is Howell-Moore's theorem. So let me just restate Howell-Moore's theorem and conclude that it actually gives mixing. So the statement of Howell-Moore is that if pi is unitary, strongly continuous, and ergodic, and actually this pi should be a representation of SL2R, if this guy is unitary, strongly continuous, and ergodic, then it is mixing. That is, the limit of f VW G as G goes to infinity in the group G is 0 for every V and W in H. Okay? This is Moore's theorem. And I don't have much time to prove it, so I would prefer to give some idea of the proof, but only tomorrow. But I would like to tell about the dynamical consequence of this theorem. So here's the consequence of the theorem. And it is in the same setup as this one. So if X, and here I forgot to say that, of course, gamma should be a lattice. So if X is homogeneous, in the sense that gamma is a lattice, and G, so let me remind how to state this. Okay, and G is either in the diagonal group or in U plus. And again, I forgot to say that G is not the identity. Then the Z action of G on X is mixing. So in particular, geodesic and horocycle flows are mixing. Okay? So how do we prove this? Well, the only thing we have to... naturally, you have to consider the Koopman-von Neumann representation. And you consider the Koopman-von Neumann representation, and the Koopman-von Neumann representation is going to be unitary, strongly continuous. And is it going to be ergodic or no? Yes, right? So the conclusion is that it is mixing. But you can check that if G belongs to A or G belongs to U plus, the powers of G are going to infinity in the group SL2R. Because they are going to infinity in the group SL2R, it means that the limit of this expression here is 0. And once the limit of this expression is 0, it means exactly that G is acting in a mixing way in your space. Okay? So this is, unfortunately, I didn't have time to prove Moore's theorem. I don't know where my head was when I thought that I would prove Moore's and Furstenberg's theorem. But you can check on the lecture notes. The lecture notes has the proof of Moore, has the proof of Furstenberg's. Maybe tomorrow, depending on the way that I organize the talk, I'm going to talk a little bit about the proof of this theorem. But the conclusion that I want you to have from today is that SL2R is very interesting, and it has a lot of rigidity results. And the main property that we used was, again, that the geodesic flow renormalizes the horocycle flow. This was the way that we proved the mountainous phenomenon, and mountainous phenomenon gave to us ergodicity. To get mixing is just a matter of some calculations and some functional analysis lemmas. Okay? Do you have any questions? Okay, so tomorrow we are going to talk about Oppenheim's conjecture. And I aim also to do some background for Alex that he's going to speak. Remind you, he's going to speak next Tuesday and next Thursday at the same time. Okay? So see you tomorrow.